But what does a hawk see? Eyes. It's easy to take them for granted. But what if you think of them as machines using one particular range of wave energies to produce high-quality images? Inside an eyeball, well, not quite. It's actually a building called a camera obscura, but it works just like an enormous eye. Here's the image, a picture of the world outside. It can be steered from side to side just as we would look around. Here's the camera obscura from the outside. Doesn't look much like an eye, so I believe it works like one. Let's take a look at the optics. The light is deflected into the tower by a mirror. It passes through a hole, then it's focused by a glass lens onto the curved screen. There's no mirror in an eye, and the lens isn't made of glass, but the elements are the same. Camera obscura, eye, two imaging systems both using the same energy source. Here's another, a normal film camera. Now you should be able to see how it resembles the other two. A lens to focus the light and make the image sharp. There's a hole or aperture. It varies in size. In our eyes, it's called the pupil. It adjusts the amount of light passing through the system. This is the effect. Right, we've got three things in common. What else is there? Any imaging system needs something which detects the incoming energy. Film undergoes chemical changes when exposed to light. What kind of film do we have at the back of our eyes? It's called the retina, and it's made up of thousands of cells like these. Light is absorbed by coloured pigments in the cells, and they produce electrical signals. This is an electron microscope picture of the base of one cell. The electrical signals cause tiny amounts of chemicals to be released on the surface of other cells, generating thousands of electrical pulses which are sent onto the brain. Film in the camera, a retina in the eye, similar but not the same. So how different are they? A strange thing to see at the end of a snooker table? Maybe. Think colour. We all know snooker needs a sharp eye. But try playing it in black and white. Not so easy, huh? And for those of you watching in black and white, the red is to the left of the green. Foul shot, green ball potted, 4 away. We all need to be able to tell the difference between colours. But what is colour? A beam of light looks white before it hits this prism. But on the other side are all these colours. How come? Light energy travels as waves. White light is a mixture of different wavelengths. Now you should be able to see why we get the spectrum. The prism bends long wavelength light more than short wavelengths. So long wavelength light is red, medium wavelengths are green, short wavelengths are blue. Simple as that? People used to think so. Now they're not so sure. To see why, look at these oranges. First on a warm summer morning. Now if we fast forward to the evening, spot the difference. No? Well, there isn't one. We all know that oranges don't change colour. But look again. These three bars show the amount of light reflected by the oranges at long, medium and short wavelengths, what we sometimes think of as red, green and blue. In the early morning, there's more short wavelength light reflected and less long wavelength. Why? Because sunlight in the morning has a high proportion of shortwave light. In the evening, it's the opposite. The oranges reflect more long wavelength than short wavelength light. The wavelengths change, but if colour is supposed to be to do with wavelength, why haven't the oranges changed colour as well? It's not as if they're blue edges in the morning and red edges in the evening. They're oranges all day. Colour has obviously got something to do with wavelength, but that can't be the whole story. Meanwhile, back to the snooker. And it's very tense in this final frame. Just like in the morning and evening with the oranges, we can change the lights shone on the table. So we can change the wavelengths reflected by the balls. But we can still tell them apart. How do we do it? Right. Try looking at the balls through red-tinted spectacles. The red balls, which normally look dark, suddenly look much lighter compared to other colours. Whatever coloured light we shine on the balls doesn't change this. White is the lightest, followed by pink and red. Now let's try a blue pair of specs. What difference will that make? The blue ball on the right looks lighter than the red ball on the left, although the white is still the lightest. The spectacles act as filters, only allowing certain wavelengths of light to pass through. White objects are those that look lightest through any filter, like the cue ball. Other colours look light through one filter, but dark through others. There's not much colour in any one of these pictures. But when we combine the effects of the three filters, hey presto, glorious Technicolor. We can produce true colour with three filters. Does that mean there are filters in our eyes? Remember these? The light-sensitive cells of the retina. The responses of the cone-shaped ones produce our colour vision. Some act like the blue filter, some like the red, and others act like the green. This graph shows how the chemical pigments in the three sorts of cone respond to light of different wavelengths. By comparing the responses of the three systems, our brains produce colour. What if we didn't have three cones? Cats don't, so what does their world look like? Well, it might look something like this. Can you think why cats don't have colour vision? These are the wavelengths our eyes are sensitive to. what's going on now? There's certainly some energy here, beyond the light spectrum. Let's call it ultraviolet, because it's beyond the violet we can see. Ultraviolet, shorter or longer in wavelength than visible light. Insects are sensitive to ultraviolet light. A bee's world might look something like this. Flowers reflect ultraviolet, which attracts the bee. This helps pollination. Ultraviolet is used by insects to live, but we can use it to kill them. This lamp emits ultraviolet. The flies are attracted to it. Little do they realise the wire grid is electrified. One touch and good night Vienna. That takes care of the short wavelengths. How about beyond the other end of the visible spectrum? This burglar alarm is detecting something near red. We can't see this infrared, but we can make machines that can. It's no joke trying to find someone trapped in a smoke-filled room or a collapsed building, especially if you're the one under the rubble. But bodies emit heat energy at infrared wavelengths. Now the emergency services carry cameras like this, which detect infrared sources. This time, it was only a practice run. Next time, it could be the real thing. Some animals depend on sensitivity to infrared for survival too. No, it's not the chickens. Small pits under the eyes of this python are sense organs which detect infrared energy. What do they tell the snake? Let's watch this through an infrared camera. As you can see, the snake can locate the birds by the heat given off from their bodies. The light we see is only a limited amount of what are called electromagnetic waves. Other animals or machines, like special cameras, can produce images with shorter or longer wavelengths. How big is the family? What lies beyond infrared and ultraviolet? This is the range of electromagnetic waves, from X-rays through the visible spectrum to radio waves. Wavelength continually goes up and frequency smoothly goes down. They both change. So what stays constant? Let me introduce you to the electromagnetic family. Different, but all travelling at the same speed. From X-rays along, wavelength increases, but the whole family are the same type of wave. We can make images from any particular wavelength, but different images mean different information. First, we need to build an imaging system. You've probably used a telescope like this. It's basically a tube with 3 lenses. The light passes through the first lens, producing a magnified inverted image. This is further magnified and turned the right way out by the eyepiece. But this is a telescope too, and a much more powerful one. It doesn't use visible light, and it doesn't have lenses. So how does it work? Well, first let's look at another type of light telescope, a reflecting telescope. It doesn't use lenses either. This one is used for looking at stars, not ships. instead of a system of lenses, it has a pair of mirrors. The light from distant stars passes down the tube and is first reflected from a parabolic mirror and then by a second mirror through a hole into the eyepiece. So this telescope works in the same way, but it uses long wavelength radio waves. They are reflected from a parabolic dish to a receiver. Long wavelength radio waves, large reflecting surface. Shorter wavelength light, smaller reflecting surface. What's the connection? Anyway, what do radio pictures look like? Well, here's a normal light picture of a group of stars, and here's a radio picture. They're pretty similar, so why bother using a radio telescope? We'll take a look at this part of the sky, seen with visible light. Now try a radio telescope. Those coloured areas are stars which emit a large amount of radio waves, but no light at all. Without this kind of image, we'd never know they were there. Now you've seen images from the long wavelength members of the family, what about the other end of the spectrum? Here's a picture you're probably used to, an X-ray of someone's spine. The X-ray will produce an image on photographic film, having passed right through the patient's body and the table. The beam of X-rays is produced from a point source above the patient. There isn't a focusing system. Can you think why X-rays are difficult to focus? And what has that to do with the radiographer standing behind a thick protective shield? Our eyes provide familiar pictures of the world we inhabit. New machine imaging systems, new ways of seeing. The Earth from space. A beautiful picture, but it doesn't tell the whole story. Here's a satellite photograph recording infrared emissions from the Earth. The different temperatures of the seas and land are shown as different colours. Paris, France, by satellite, photographed in infrared. Built-up areas are blue, agricultural land and parks show up as red. Want to know who farms or builds what, anywhere in the world? No problem. Want to understand the processes of the weather? Satellites coming here too. This is Hurricane Gilbert passing over the Caribbean in 1988. Images like this help to predict damage. We've seen that producing images is vital for survival of animals. Worries about global changes in the climate are increasing. Maybe producing new images will be vital to our survival too.